Hello everyone, welcome back. Today we are tackling yet another interesting linked list problem. Merge k-sorted lists, Leetcode 23. Although it is classified as hard, it is on the easier side of hard level questions. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an array of k linked lists and each linked list is sorted in ascending order. And our goal is to merge all linked lists into one sorted linked list and return its head. Then in example 1, we are given 3 linked lists with head nodes as 1, 1 and 2. And each head node is connected to its respective linked list. For example, the first list has additional nodes 4 and 5, and the second list has additional nodes 3 and 4, and the third list has additional node 6. And the goal is to merge all of these linked lists into a single linked list and return its head such that the values stay in the ascending order. So for example, here we will get the list as 1, 1, 2, 3, 4, 4, 5, 6, which we will return as the answer. Now in terms of solution, one of the simpler naive approach can be to sequentially merge two lists at a time. For this, we can reuse our solution for merging two sorted lists. Let's quickly recap how we merge two sorted lists. Let's ignore this list for now and merge these two lists. To merge them, we first initialize the merged list or our answer with a dummy node. This dummy node helps us avoid edge cases such as dealing with an empty list or inserting directly at the head and provides a straightforward way to start. From here, we build the merge list step by step. To do this, we traverse both lists simultaneously, comparing the values of the current nodes and pointing the answer to the node with the smaller values. For example, for these two nodes, it doesn't matter as both the values are 1. So, dummy node can point to either of the nodes. So, suppose it pointed to this node. And then we move forward the iterator in list 2. And now, since 1 is smaller between 1 and 3, the merge list links this one. And we move forward the iterator to next node in list 1. Now between 4 and 3, since 3 is smaller, we link it to the merge list and move the iterator forward. And between these two 4s, we can pick any. Suppose we pick this one and then we move this iterator forward. And finally the iterator for list 2 reaches the end. So now we append the remaining nodes 4 and 5 from list 1 to the merge list since no nodes are left in list 2. So this summarizes the basic idea behind merging two sorted lists. Now we can reuse this solution to iteratively merge multiple sorted lists. Here we start with an empty list, let's call it answer, and merge each list into answer using the method for merging two sorted lists. So we will first merge answer with list 0 and get the result same as list 0 with elements 1, 4 and 5. Next we will merge answer with list 1 with elements 1, 3 and 4. So the list becomes 1, 1, 3, 4, 4, 5. And then we will merge list 2 with elements 2, 6 with the answer. So finally our answer becomes 1, 1, 2, 3, 4, 4, 5, 6. Now while this approach works and is straightforward, it is far from efficient. Each merge operation takes O of n time. And since we are doing it for k list, that takes O of n into k time. However, the space complexity stays O of 1 because we are merging the list in place. Now the naive approach is slow because it merges the list sequentially. So suppose we have more lists here. Then first we merge list 1 to answer. Then we merge list 2. Then we merge list 3. Then we merge list 4 and so on. And this creates a long chain of merging operations equal to number of lists. But a better approach is to use merge sort logic, which divides and conquers by pairing lists systematically. So for example, we will first merge these two, then these two, then these two and so on. And when this is merged, then we merge these two. And finally, we get a single merge list, reducing the chain of operations to just log of k. Because at each merge step, the number of lists is halved. Now, the first step in the merge sort logic will be the divide step. where we will split k lists into two halves. For example, if we have 7 lists, then we can split them, for example, into 4 lists on the left and 3 lists on the right, forming two subsets, and recursively continue until each subset has only 1 or 2 lists remaining. And now if the subset has only one list, then it is already considered merged because there is only one list remaining. But if the subset has two lists, in this case, we will merge them using merge two sorted list solution that we discussed earlier and get a single list and repeat this process recursively until we hit the base case, which is where we have only one list remaining. At this point, all the lists are fully merged and we return that merged list as our answer. For example, here for k equal to 3, we split this array into two lists, left and right. Although here it's coming up like bottom and up, but basically these two lists on the left and this one on the right. So we merge these two lists and get the answer as 1 1 3 4 4 5. And on the right side there is only one list, which is 2 6, so it is already considered merged. And now we will merge these two lists to get our final answer. Now the time complexity of this approach is O of n log k, as the depth of the recursion in case of this merge sort logic will be log of k, because at each merge step the number of lists is halved and merging the two lists take O of n time, resulting in overall time complexity as O of n log k, and the space complexity will be O of log k as well, mainly coming from recursion stack depth. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, we call the merge sort helper function, passing the entire array of linked lists along with its starting index and ending index. This function uses divide and conquer logic to recursively split the array into two halves and merge the resulting pairs until all lists are combined into a single sorted list. Now inside this function, first we check for the base case, which is when start is equal to end. At this point, there is only one linked list remaining, which we can return because it is already merged and sorted. Otherwise, if start index exceeds end index, it indicates an empty segment, that is, there are no lists remaining to merge. Hence, we can return null in this case. And now comes the divide step. So first we calculate the midpoint of the current range and recursively call this helper function on the left half of the list, that is from start to mid, and right half of the list from mid plus 1 to end, and store the results in respective variables. And once the divide step is complete, we come to conquer step, where we will merge left and right lists using the helper function merge two lists and return this combined list. We have already covered this function in a different video, merge two sorted lists. Please check out the I button for that. So far, we have been merging lists pair by pair in both the naive and merge sort based approaches, reusing the solution for merging two sorted lists. This involves implementing two methods during an interview, which can be a bit challenging. Now let's look at heap or priority queue based approach, and more specifically the min-heap based approach. In merging two sorted list solution, we were finding the minimum across just two lists, making it straightforward to compare and select the smallest element. However, since we now need to repeatedly find the minimum across multiple lists, a min-heap becomes a perfect fit for efficiently handling this task. Because with a min-heap containing k elements, inserting an element or extracting a minimum from it takes just O of log k time. So first we create a min-heap and then insert head of all k linked lists into the heap. So we will insert the heads 1, 1 and 2. And then we extract the smallest element from the heap and append it to the result list, again starting with the dummy node to simplify edge cases like inserting at the head. So for example, here we extract node 1 from it and append it to the list. Let's assume this one comes from list 1. And as we are not done with this list yet, we will insert the next node of this minimum element into the heap. Here for example, that is node 4. So we will insert it into the heap. And we will repeat this process of extracting the minimum element, appending it to the answer list and inserting the next node into the min heap until the heap is empty. At this point, all nodes from all k lists have been processed and we can return the merge list as the answer. So continuing further, we will again extract the minimum element, this time from list 2, and append it to the list and insert its next element, which is 3, into the min heap. And again we extract the minimum element, which this time is 2, and append it to the list and insert its next element, which is 6, into the min heap, and repeat this process of extracting the minimum element, this time 3, appending it to the list and inserting the next element, which is 4, into the heap, and again extract the minimum element, which is 4 this time, and append it to the list and say it comes from list 1. So we will insert the next element, which is 5, into the heap, and again extract the minimum element, which is 4 this time, coming from list 2, and append it to the list. So now no further nodes remain in list 2, so no insertion happens, and heap has just 2 elements now, 5 and 6, coming from 2 remaining lists. So again we extract the minimum, which is 5, so we append it to the list, and now there are no further nodes remaining in list 1, and again we extract the minimum element, which is 6, and we insert it into the list. And now since 6 also doesn't have a next element, we are done with this list as well. And now the min heap is empty. So at this point, we can return this merge list as our answer. Now the time complexity of this approach is O of n log k, because inserting an element and extracting a minimum from the heap takes O of log k time, where k is number of lists, and we are doing it for n nodes across all lists. Hence the overall time complexity will be O of n log k, and the space complexity will be O of k, because we are storing at most k elements at any given point in the min heap. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, let's initialize an empty min heap. In Java, we can use priority queue for that, where we can pass in the custom comparator. For example, here we are telling it to compare the list node objects by their value attribute. However, in Python, we are storing the value, the index of the list, and the node itself. Why do we do that? We will get to it in just a moment. Now we will insert the head nodes of all the lists into this heap, where in case of Python, what we are doing is a bit special. The reason for this is list node objects themselves are not inherently comparable, as the class does not have any implemented comparator method. In Java, for example, we are passing the custom comparator method, but here we don't have this luxury. So to fix this in Python, one way could have been that we insert all the node values, which are integers, into the heap, which will result in O of n space, which we don't want. So another way could have been that we would have written the wrapper class for list node, say list node wrapper, and implemented this custom comparator method. And then inserting this wrapper node into the min heap wouldn't have been a problem, because heap can now perform comparison between the objects. But that introduces complexity by requiring additional class and also the overhead of creating the new instance every time we use the list node object. But a more Pythonic way can be that we use tuple here, where we could have just inserted the value and node. But the way the Python heap works is that in case of a tie, when the node values are equal, it tries to compare the list node objects directly. And again, the list node class doesn't have a custom comparison method, which leads to type error. So a better solution is to include the index of the list as a tiebreaker. With this, the heap will resolve ties by choosing the entry from the list with a smaller index, ensuring consistent behavior. So from here on, the logic is very similar. After populating this heap, we can initialize a merge list with a dummy node to simplify the edge cases and build the result step by step. Let's also initialize the answer pointer, which will help us iterate over this merge list. Now, while this min heap is not empty, we will extract the smallest value from the min heap and append this extracted node to the answer list by setting the next pointer of answer to this node and advance the current pointer in answer to the next node. Now, if this extracted node has a next node, we will insert it into the min heap. And once this min heap is empty, meaning all nodes have been processed from all lists, we will return dummy.next as our answer. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.